Greetings, everyone. Welcome aboard our comprehensive exploration of CVD basics, curated exclusively for you by Semi-Slides. I'm Semi-Sherpa, your trusted guide, eagerly prepared to lead you through the maze of chemical vapor deposition, CVD, technology. Whether you're a seasoned engineer, an eager student, or a professional venturing into the semiconductor arena, this series promises to serve as a rich trove of knowledge. We aim to catalyze a profound understanding of CVD technology's pivotal principles and broad-ranging applications. Together, we'll journey through the intricate labyrinth of semiconductor processes that revolve around CVD. Our exploration will span crucial areas such as thermal CVD, plasma-enhanced CVD and HDP, area-selective CVD, selective epitaxial growth, and even delve into the realm of CVD equipment. So, prepare to dive headlong into the fascinating universe of CVD basics, a fundamental pillar within the world of semiconductor manufacturing. Secure your intellectual harness for an expedition as enlightening as it is thrilling. Are you geared up for the leap? Let's dive deep. Chemical vapor deposition, CVD, physical vapor deposition, PVD, and atomic layer deposition, ALD, are leading techniques for thin film deposition, each with unique characteristics and strengths. CVD, being a highly versatile process, offers superior step coverage, making it ideal for depositing films on complex geometries. It also allows precise control over film thickness and composition, with the ability to incorporate dopants into the film, rendering it indispensable for semiconductor manufacturing. However, the high-temperature nature of the CVD process can be a challenge. Contrary to what was previously mentioned, CVD typically operates at higher temperatures than PVD. These high temperatures can affect substrate integrity, especially in heat-sensitive applications. Also, the CVD process is susceptible to film impurities resulting from precursors with elements such as carbon, C, oxygen, O, and chlorine, Cl. This factor necessitates stringent precursor purity and process control to minimize impurities in the resulting film. Another challenge is the higher frequency of chamber cleaning, due to the tendency for unwanted deposition on chamber walls. In addition, the cost of consumables, COC, for CVD is often higher than that for PVD, considering the precursor's price and their lower utilization efficiency. Moreover, CVD processes often involve toxic gases, necessitating stringent safety and handling protocols. More challenge associated with CVD is the complexity of process control, given the number of variables involved including temperature, pressure, gas flow rates, and precursor ratios. This complexity can impact reproducibility and consistency, critical in high-volume manufacturing settings. Comparatively, PVD processes generally offer higher material utilization efficiency and do not usually require the use of toxic gases, leading to lower operating costs. However, PVD struggles with step coverage and can't match CVD's control over film properties. Lastly, ALD offers excellent control over film thickness down to the atomic level, and excellent conformality, even surpassing CVD. However, ALD is typically slower and more expensive per unit area than CVD due to the sequential nature of the process. The choice between CVD, PVD, and ALD depends on the specific deposition process requirements, considering factors like desired film properties, substrate characteristics, cost, safety, and process control considerations. Chemical vapor deposition, CVD, is a highly versatile process that can be adapted and classified in various ways depending on the specific requirements of the task at hand. The array of classifications allows for the broad utilization of the CVD technique across diverse applications, primarily in silicon fabrication, where low temperature, low pressure, thermal CVD, and plasma-enhanced CVD, PECVD, are prominently used. One of the principal classification criteria of the CVD process is the temperature. The deposition temperature ranges from ultra-high to low levels, with each category serving specific applications. High-temperature processes facilitate fast reaction rates and high-quality crystalline films, whereas low-temperature processes, often used in semiconductor manufacturing, limit damage to sensitive device structures. Pressure is another crucial classification factor, with CVD processes occurring at atmospheric pressure, subatmospheric, low pressure, or even ultra-vacuum conditions. Each pressure regime allows for different reaction kinetics and mass transport characteristics, affecting the deposition rate and film properties. For instance, low-pressure CVD is often used to achieve high film uniformity and deposition rates while reducing unwanted gas phase reactions. The design of the CVD chamber, whether it's a cold-wall single-wafer tool or a hot-wall batch furnace tool, also differentiates the process types. Single-wafer tools allow for high process control and fast process changes, while batch furnaces enable high throughput by processing many wafers simultaneously. Further classification arises from the nature of the precursors, either inorganic or metal-organic. Metal-organic precursors are often used in metal-organic CVD, MOCVD, processes to deposit compound semiconductor materials, while inorganic precursors are widely used for elemental and compound film deposition. The deposition time, continuous, discontinuous, or pulsed, is another classification metric. Continuous deposition processes are widely used for their simplicity and high deposition rates. However, pulsed or cyclic methods offer better control over film properties and interfaces, such as in atomic layer deposition, ALD, a variant of CVD. Lastly, the activation manner, whether thermal, plasma, laser, photo, combustion, or catalyst, defines the CVD process. Each method employs a different way of activating the chemical reactions that deposit the film, thereby influencing the process's efficiency, film properties, and system design. The choice of precursor and gas flow method can significantly vary depending on the desired deposited film material, enhancing the process's adaptability. This expansive categorization of CVD processes illuminates its flexibility and broad utility, offering distinct pathways for optimizing thin film deposition across a wide array of materials and applications. Chemical vapor deposition, CVD, is a vacuum deposition method that plays a crucial role in various areas of material science and engineering, including the fabrication of semiconductors, optical devices, and protective coatings. It leverages the properties of one or more volatile precursors that undergo a chemical reaction to produce a solid material, which deposits as a thin film onto a substrate. A typical CVD process takes place within a specialized chamber. Inside the chamber, the substrate onto which the film is deposited is placed on a holder, also known as a susceptor. This holder can rotate or move in other ways to ensure even film deposition across the substrate's entire surface. Additionally, heaters are incorporated into the chamber to provide the necessary thermal energy for the chemical reactions to occur. These heaters can be direct contact types or indirect types like radiant heaters. For some CVD processes, the heaters can reach temperatures of up to 1000 degrees Celsius or higher. Precise temperature control is vital for achieving the desired film characteristics, as it can influence the reaction rate, film uniformity, and film composition. On the other side of the reaction, the byproducts produced are evacuated from the chamber through an exhaust system. This exhaust system typically involves a vacuum pump, which maintains the chamber at low pressures conducive to the CVD process, and a scrubber. The scrubber is a critical part of the system as it removes potentially harmful substances from the exhaust before releasing it into the atmosphere. The scrubber often uses a washing process, chemically reacting with the byproducts to neutralize them or convert them into less harmful forms. Maintaining the cleanliness of the exhaust system is important as any residue can contaminate future deposition processes. The volatile precursors are introduced into the chamber through a showerhead-like structure or an injector, which is designed to distribute the precursors evenly across the substrate surface. In most CVD systems, the precursors are carried into the chamber with a carrier gas, which can also play a role in the chemical reactions. Precursors can be delivered as liquids or solids through vaporization before being introduced into the chamber. As the precursor and reactant gases encounter the heated substrate, they react or decompose, forming a film that deposits onto the substrate. This reaction can be generalized as AX, gas, plus BY, gas, leading to AB, solid, plus XY, gas, where the gaseous precursors AX and BY react to form the solid film AB and the volatile byproduct XY. The type of film, monocrystalline, polycrystalline, amorphous, or epitaxial, depends on the specific precursors used and the process conditions. Some common films deposited by CVD include silicon-based films such as silicon dioxide, silicon carbide, silicon nitride, and silicon oxynitride, carbon films like ACL, and metals such as tungsten and titanium nitride. High-K dielectrics are also often deposited using CVD for applications in microelectronics. Chemical vapor deposition, CVD, involves a series of chemical reactions that transform volatile precursor gases into a solid film on a substrate. These chemical reactions fall into several categories based on the mechanisms and types of reactions involved, including pyrolysis, reduction, oxidation, nitridation, carbonization, and hydrolysis. Pyrolysis is a process where the precursor is thermally decomposed to form a solid deposit on the substrate. The high temperatures typically used in thermal CVD readily drive the pyrolytic decomposition of the precursor, leading to film growth. Pyrolysis reactions are common in CVD processes using inorganic precursors like silane gas to deposit silicon films. Reduction and oxidation reactions involve the transfer of electrons from one species to another. In reduction CVD, the precursor is reduced on the substrate's surface, often by hydrogen or another reducing agent. This reduction process can be used to deposit metals from their gaseous inorganic or metal-organic compounds. Conversely, in oxidation CVD, the precursor is oxidized to form a solid deposit. Oxidation reactions are often used to grow oxide films, such as silicon dioxide or aluminum oxide, from inorganic or metal-organic precursors. Nitridation is a process where a precursor reacts with a nitrogen-containing species to form a nitride film. This type of reaction is commonly used in the deposition of nitride films, such as silicon nitride or gallium nitride, which are important materials in electronics and optoelectronics. Carbonization refers to the transformation of organic precursors into carbon or carbon-containing films. During this process, the organic precursors decompose, and the non-carbon elements are typically removed as volatile byproducts. Hydrolysis is another chemical reaction mechanism in CVD, where a precursor reacts with water vapor to form a solid deposit and typically a gaseous byproduct. This process is commonly used to deposit oxide films from metal-organic precursors. Each of these reaction types provides a pathway for transforming gaseous precursors into solid films, and the choice of reaction type will depend on the desired film material, the available precursors, and the specific requirements of the process. Chemical vapor deposition, CVD, is a high-precision deposition process, and the method of precursor and reactant gas supply is critical to the outcome of this process. In a typical CVD and PECVD setup, both the precursor and reactant gases are introduced simultaneously. They react on the substrate's surface to form a solid film. The thickness of the deposited film progressively increases over time as more gas is supplied and the reaction continues. This process affords continuous growth of the film, and the deposition rate directly depends on the rate of the chemical reaction, the concentration of reactant gases, and the process temperature and pressure. Sequential CVD is a variant of the CVD process where the precursor and reactant gases are introduced sequentially, similar to ALD, but the level of control and the growth mode differ. The precursor is first introduced to react with the substrate surface, after which the reactant gas is introduced. Unlike ALD, which aims to achieve atomic layer precision by fully saturating the surface with each precursor pulse, sequential CVD allows for sub-monolayer to multiple layer growth in each cycle depending on the exposure time and concentration of reactant gases. Cyclic CVD, on the other hand, employs a distinct method of gas supply. Here, the precursor and reactant gases are not continuously introduced but supplied in a pulsed manner. Each pulse of precursor and reactant gases results in a deposition phase, followed by a short dwell time before the next pulse is introduced. Unlike atomic layer deposition, ALD, cyclic CVD does not incorporate a purge step in each cycle. As such, some reactant species may remain on the substrate surface or within the chamber during the dwell time, possibly leading to less precise control over the film growth compared to ALD. Each of these techniques, CVD, cyclic CVD, and sequential CVD, provides unique benefits in terms of speed, precision, and quality of deposition, enabling a wide range of applications across different materials and devices. The choice between these techniques will largely depend on the specific requirements of the process, such as the desired film thickness, uniformity, and material properties.
Chemical vapor deposition, CVD, is a method of depositing desired films on a substrate by inducing chemical reactions from the supplied gaseous precursors. This complex process follows a sequential order of steps that ensure the efficient and controlled deposition of the target film. Step 1. The initial step involves the transport of reactant gases to the reaction chamber. The mass transport of reactants is critical to ensure the reactants reach the substrate surface in sufficient quantities to drive the deposition reaction. This phase involves the careful control of gas flow rates and pressures to achieve a consistent and uniform supply of reactant gases. Step 3. Following the mass transport of reactants, the diffusion of precursors occurs in the gas phase. This is where the precursor gases spread from areas of high concentration to areas of lower concentration, reaching all areas of the substrate surface. Step 4. Once the precursors have diffused adequately, they are adsorbed onto the substrate surface. This adsorption process is vital for enabling the subsequent surface reaction. The adsorption of precursors depends on the interaction between the precursor molecules and the substrate surface, which can be influenced by parameters such as temperature and pressure. Step 5. With the precursors adsorbed on the surface, they undergo surface diffusion, where they move across the substrate surface to find suitable sites for reaction. This surface diffusion process is an essential step in ensuring a uniform and high-quality film deposition. Step 6. The surface reaction then takes place, where the adsorbed precursors react to form the target film on the substrate. This step is influenced by various factors, including temperature, pressure, and the specific chemistry of the precursors and the substrate. Step 7. The desorption of the byproduct, a natural result of the surface reaction, happens next. These gaseous byproducts need to be effectively removed from the substrate surface to prevent them from interfering with the ongoing deposition process. Step 8. Finally, the byproducts are transported away from the reaction site by gas phase diffusion, and then they are evacuated from the chamber. This removal ensures a clean environment for the next deposition cycle to occur, maintaining the purity and quality of the ongoing film growth. Adsorption is a fundamental process in chemical vapor deposition, CVD, that controls the initial stage of the deposition process. During this phase, gaseous species interact with and adhere to the substrate surface. This interaction can primarily take two forms: physisorption and chemisorption. Physisorption, also known as physical adsorption, is a process in which the gas molecules weakly bind to the substrate surface primarily due to van der Waals forces. This interaction is typically reversible, as the forces involved are weak, and the gas molecules retain their chemical identity without any chemical transformations occurring. The process is exothermic, releasing energy, and is typically associated with lower translational energies of the incoming gas molecules. On the other hand, chemisorption or chemical adsorption involves the formation of a chemical bond between the gas molecules and the substrate surface, leading to stronger and more specific interactions. This process is typically irreversible under CVD conditions due to the strength of the newly formed bonds. Chemisorption can occur either through direct dissociation, where the gas molecules break apart upon hitting the surface, or through precursor-mediated chemisorption, where a precursor molecule first adsorbs onto the surface and subsequently reacts to form the desired deposition material. Interestingly, the transformation of gaseous species to atomic bonds on the substrate surface during CVD can proceed via various pathways. This could involve a stepwise transformation from physisorption to chemisorption and finally to atomic bonding, a more direct transformation from chemisorption to atomic bonding, or even directly forming atomic bonds. The formation of these atomic bonds is a prerequisite for the surface reaction to proceed, enabling the deposition of the desired material. Understanding these mechanisms and differentiating between physisorption and chemisorption is vital for controlling the deposition process in CVD. The nature of adsorption, whether it be physisorption or chemisorption, can significantly influence the uniformity, quality, and properties of the deposited material, making this a central area of study in CVD research. Understanding the temperature dependency of homogeneous and heterogeneous reactions in the context of chemical vapor deposition, CVD, processes can be instrumental in optimizing film deposition. Using the deposition of silicon from silane, SiH4, as an example provides a more concrete understanding of these concepts. In a CVD process, silane is introduced into a reactor chamber where it's expected to react at the substrate surface, forming a layer of silicon. This reaction is intended to be heterogeneous, that is, it occurs at the interface of the gas phase and solid phase, between the silane and the substrate surface. The direct reaction of silane on the substrate surface leads to a uniform and high-quality silicon film. However, the rate of this surface reaction, and therefore the quality of the film, is heavily dependent on the substrate temperature, as higher temperatures can accelerate reaction rates. Conversely, at higher temperatures or with excess silane, homogeneous reactions can become prominent. These reactions occur entirely within the gas phase, with silane molecules reacting with each other before reaching the substrate. These reactions are generally undesirable in the context of CVD processes. While they effectively consume silane, they produce silicon-containing particles in the gas phase that can deposit as rough, non-uniform films, reducing the overall film quality. Additionally, silane consumption in the gas phase reduces the amount available for surface reactions, potentially leading to a mass transport limited regime where the reactant delivery rate to the substrate becomes the limiting factor in the deposition process. In essence, the desired heterogeneous reactions are favored at lower temperatures, where they produce uniform, high-quality films, while the undesirable homogeneous reactions are more likely at higher temperatures, leading to non-uniform film deposition and inefficient reactant use. Therefore, temperature control, in tandem with reactant supply management, is key to promoting the desired reaction type and ensuring efficient, high-quality film deposition. Comprehending the intricate dynamics of gas flow is integral to achieving high-quality film deposition in the chemical vapor deposition (CVD) process. The Poisson flow concept illuminates these dynamics, focusing on the flow of viscous fluid within a long, cylindrical pipe. This flow type is distinguished by a parabolic velocity profile, where the peak velocity occurs at the pipe's center, and velocity drops to zero at the pipe walls owing to the no-slip condition. The primary propellant for Poisson flow is a pressure gradient along the pipe, fostering a steady, laminar fluid flow. The concept of laminar flow is integral to this process. Here, the gas molecules glide in an orderly manner, parallel to the CVD chamber's walls. This well-ordered, disturbance-free flow provides an ideal environment for optimal gas-to-surface interaction. A crucial aspect of this gas flow dynamic is the no-slip condition. Because of this, gas molecules in direct contact with the substrate or chamber wall adhere to the surface and come to a standstill, resulting in a stationary layer of gas known as the surface stick layer at the solid boundary. The birth of the boundary layer is prompted at this point. The motionless surface stick layer applies a viscous force on the adjacent fluid layer, decelerating it. This slowed fluid layer echoes a similar effect on the subsequent fluid layer, lowering its velocity further. This chain reaction unfolds across multiple fluid layers, spawning a velocity gradient from the stationary surface stick layer to the swift-moving gases distant from the surface. This gas velocity gradient from the substrate to the free stream characterizes the boundary layer. Within the boundary layer, the slowed gas velocities near the surface allow the diffusion of reactant gases to prevail over convective gas flow. This critical shift facilitates the interaction of reactant gases with the substrate, steering film formation and growth. In chemical vapor deposition, or CVD, the process of precursor and reactant gases diffusing to the wafer surface through the boundary layer is referred to as mass transport. Conjointly, the process of film growth on the wafer surface, which occurs when the precursor and reactant gases meet, is called surface reaction. Since these two processes take place sequentially, the relatively slower process between the two becomes the rate-determining step and governs the overall reaction speed. In other words, if mass transport is slower, the process is deemed under mass transport control. If the surface reaction is slower, it's considered surface reaction control. When mass transport control comes into play, the growth rate is defined by the speed of reactant species delivery to the substrate surface. Predominantly encountered in high-pressure and high-temperature CVD processes, the precursor concentration at the substrate surface becomes the rate-limiting step. In this scenario, the deposition rate is bound by the concentration of the reactive species in the gas phase. If the substrate surface is starved of reactant species, it results in a slower growth rate, particularly when the gas source is distant from the substrate surface or the gas flow rate is significantly low. Conversely, under surface reaction control, the reaction rate on the substrate surface governs the growth rate. This control mechanism is typically found in low-pressure, low-temperature CVD processes. Here, the reactant species readily reach the substrate, but the rate of their reaction to form a solid film on the surface becomes the limiting factor. An increase in temperature under this control can augment the deposition rate as it enhances reaction kinetics. However, an excessively high temperature may lead to undesirable consequences, such as a rough film surface or the premature decomposition of the reactant before reaching the substrate. In the chemical vapor deposition, CVD, process, temperature plays a pivotal role in the interaction of reactant transport and surface reaction, two primary factors in achieving optimum film deposition. When we explore the influence of temperature on the process dynamics, it's evident that it considerably impacts the reaction mechanisms, thereby dictating the overall rate of deposition. At elevated temperatures, the reactants, inclusive of precursor molecules, are supplied with ample energy, resulting in more frequent and more vigorous reactions. This heightened energy state often gives rise to homogeneous reactions within the gas phase, even before the reactants have the opportunity to interact with the substrate surface. As a result, reactants are predominantly consumed within the gas phase, causing the availability of reactants for surface reactions on the substrate to dwindle. Under these circumstances, where the rate of surface reaction is so high that the transport of reactants can't keep pace, the process leans heavily towards mass transport control. In such a scenario, the rate of film deposition is chiefly reliant on the rate at which reactants can be transported to the substrate surface. As a consequence, the uniformity of and wafer thickness of the deposited film is significantly impacted by the flow of gas. Hence, designing hardware, such as showerheads, to promote a consistent gas supply, becomes vital in achieving uniform film thickness within wafer. On the other end of the temperature spectrum, in a low-temperature CVD process, the rate of surface reaction considerably declines. Under these conditions, the reactants are not as readily consumed within the gas phase as they would be in a high-temperature environment. This surplus in reactant supply induces a shift in the process regime, moving towards a scenario where the surface reaction rate governs the film growth rate, a situation referred to as surface reaction control. In this regime, the majority of the reaction transpires on the substrate surface, leading to heterogeneous reactions. Consequently, the uniformity of wafer thickness is largely influenced by the uniformity of the wafer temperature, emphasizing the importance of hardware like a chuck, which ensures consistent wafer temperature. Determining whether a CVD system operates under mass transport control or surface reaction control can be accomplished through a simple experiment, involving the manipulation of the gas supply. If a doubling in gas supply corresponds with a doubling in growth rate, it likely indicates mass transport control. In contrast, minimal or no change in the growth rate might suggest surface reaction control. Such an experiment proves invaluable in effectively controlling and optimizing the CVD process. In the realm of thin film deposition, step coverage is a critical metric to ensure the high performance of microelectronic devices. The concept pertains to the uniformity of film thickness across a substrate, even over the intricate topographies such as steps, trenches, or holes. The degree of step coverage is often influenced by a complex interplay of physical properties, reaction rates, deposition temperature, and the concentration of reactants. Step coverage is largely characterized by its conformality, a term that reflects how well the deposited film conforms to the substrate surface features. A fully conformal film demonstrates a uniform thickness across all surfaces. In contrast, a non-conformal or subconformal deposition is when the thickness varies across different features. On the other hand, superconformal deposition refers to a unique scenario where the film thickness is greater at the bottom and sides of high aspect ratio features compared to the top surfaces. An aspect ratio is another significant factor that impacts step coverage. It is the ratio of the depth to the width of a feature, such as a trench or hole. High aspect ratio features are particularly challenging for achieving good step coverage because the reactant gases need to penetrate deep into the features to ensure uniform film deposition. Voids and seams can be formed during the film deposition in high aspect ratio features. Voids are empty spaces within the film that may form if the deposition rate on the top surfaces is higher than the bottom, causing the top to close off before the feature is fully filled. Similarly, a seam is a narrow gap that forms when two growing films meet and cannot completely fill the feature. Understanding and controlling these phenomena is crucial to achieve optimal step coverage. Different deposition methods such as physical vapor deposition, PVD, chemical vapor deposition, CVD, and electroplating have varying success with step coverage. PVD, being a largely directional process, often struggles with step coverage, especially on the sidewalls of features and in high aspect ratio structures. CVD and electroplating, on the other hand, can provide better step coverage due to their more isotropic nature, but they can face challenges in filling high aspect ratio features without forming voids or seams. Therefore, a strategic choice and careful optimization of the deposition method are essential to achieve high-quality step coverage. In chemical vapor deposition, CVD, step coverage, the even deposition of a film across a substrate surface, including its intricate structures, is pivotal to achieving high-performance devices. The process is predominantly regulated by two controlling mechanisms, mass transport control and surface reaction control. Each contributes to the step coverage in a distinctive manner, shaping the quality and uniformity of the deposited film. Mass transport control governs the rate of deposition based on the delivery of the reactant to the substrate. While this provides decent coverage on flat surfaces due to a uniform deposition rate, it poses challenges for substrates with complex topography. High aspect ratio features like trenches or vias introduce the risk of limited reactant delivery, causing poor step coverage at the bottom. Reactant gas molecules, colliding and depositing on feature sidewalls, can obstruct further molecules from reaching the base, leading to the potential formation of voids and reduced conformality. Conversely, under surface reaction control, the deposition rate is dictated by the surface reaction rate of reactants on the substrate. In this scenario, even if reactant molecules encounter the sidewall of a feature, they may not react immediately and instead diffuse to the bottom, providing better step coverage for high aspect ratio features. Consequently, the film deposited under surface reaction control is typically more conformal, as the rate is defined by the uniformly distributed surface reaction probability, not the spatial distribution of reactant molecules. In surface reaction control during a chemical vapor deposition (CVD) process, the transport of reactant molecules to every nook and cranny of the substrate prior to reaction offers a theoretical path to achieve 100% step coverage, even with substrates having high aspect ratio features. Yet, in real-world scenarios, multiple factors limit this ideal outcome. Diffusion of reactant molecules in deep trenches or vias can be significantly hindered, leading to an uneven distribution of reactants and less than perfect step coverage. Similarly, some reactant molecules may prematurely react upon collision with the sidewalls of the feature before they can diffuse to the bottom, thereby contributing to non-ideal step coverage. In addition, the sticking probability, or the likelihood that a molecule will adsorb onto the surface and participate in a reaction, is not uniform across the entire surface. Areas with higher sticking probabilities may have thicker deposition compared to others, which leads to non-uniform coverage. Lastly, the effects of residual gases present in the chamber can also interfere with reactant diffusion and reaction, affecting step coverage. In the realm of chemical vapor deposition, or CVD, the growth of the film can generally be categorized into three primary modes, each of which possesses distinctive characteristics and significantly impacts the properties of the film. Among them, the first mode is known as island or Volmer-Weber growth. This form of growth is observed when the forces binding the adatoms, or the atoms adsorbed onto the surface, to one another are stronger than the forces that bond them to the substrate. This bond discrepancy prompts the formation of atomic clusters or islands on the substrate surface. As the deposition of material continues, these islands gradually expand, eventually merging to form a complete film. Films generated through this growth often exhibit a high degree of surface roughness, and this mode is typically observed in systems where there is a considerable lattice mismatch between the film and the substrate. Next, we have the layer-by-layer or Frank van der Merwe growth. This growth mode operates inversely to the first, occurring when the adatoms experience a stronger attraction to the substrate than to each other. Under these conditions, the adatoms scatter across the substrate, forming a thorough monolayer before commencing the construction of the subsequent layer. This results in smooth, high-quality films and is highly sought after for applications that necessitate a uniform and defect-free film. Achieving this growth mode, however, is notoriously challenging due to the precise control required over the deposition conditions. Lastly, the layer plus island or Stransky-Krastanov growth serves as a combination of the two preceding modes. It initiates with a layer-by-layer growth until a critical thickness is attained. Beyond this point, the strain energy caused by the lattice mismatch between the film and the substrate becomes too large to manage, and the growth mode transitions to island growth. The aftermath is a few layers of smooth film followed by rough islands. This growth mode is often witnessed in systems with a moderate lattice mismatch and may facilitate the creation of quantum dots and other nanostructures. It's important to remember that the growth mode selection in a CVD process is influenced by multiple variables such as the type of materials being deposited, the substrate preparation, and the specific deposition conditions including temperature, pressure, and precursor concentration.
In the realm of chemical vapor deposition, CVD, the technique used to initiate the chemical reaction is an essential determinant of the deposition process and the characteristics of the resulting film. This reaction initiation can be broadly categorized into thermal, direct plasma, and remote plasma methods. Thermal CVD, often referred to simply as CVD, utilizes heat as the primary driver for the chemical reactions that lead to film deposition. In this process, the CVD chamber is heated to a high temperature, often several hundred degrees Celsius, causing the precursor and reactant gases to react on the substrate's surface. The high temperature provides the necessary energy for breaking the chemical bonds in the precursor molecules, enabling them to react with the substrate and each other to form the desired film. Thermal CVD is widely used due to its simplicity and versatility, but the high operating temperatures may limit its application on thermally sensitive substrates or materials. Direct plasma methods, including plasma-enhanced CVD, PECVD, and high-density plasma CVD, HDP-CVD, use a plasma to initiate the reactions. In these processes, a gas, often a mixture of the precursor, reactant, and carrier gases, is subjected to an electric field, creating a plasma. The high-energy ions and electrons in the plasma can effectively break the precursor molecules' bonds, enabling film deposition at lower temperatures than thermal CVD. This makes PECVD and HDP-CVD particularly valuable for depositing films on substrates that cannot withstand high temperatures. The key difference between PECVD and HDP-CVD lies in the plasma generation method. PECVD uses capacitively coupled plasma, CCP, while HDP-CVD uses inductively coupled plasma, ICP, resulting in a denser and more energetic plasma that allows for faster deposition rates and better step coverage. Remote plasma method, such as radical-assisted CVD, RACVD, or remote plasma CVD, RPCVD, also utilizes a plasma to initiate the reactions but in a somewhat different way. Instead of forming the plasma directly in the reaction chamber as in direct plasma methods, remote plasma methods generate the plasma in a separate chamber or remote region. The energetic species from the plasma, typically radicals, are then transported to the main reaction chamber where they react with a precursor to form the film. By separating the plasma generation from the deposition process, remote plasma methods can minimize damage to the substrate from high-energy ions and electrons, providing a gentler deposition process suitable for sensitive materials. Each of these methods, thermal CVD, direct plasma CVD, and remote plasma CVD, offers unique advantages and potential drawbacks, making each more or less suited to specific applications, materials, and device requirements. The choice between these methods requires a careful understanding of their characteristics and the desired outcome for the deposition process. In the realm of thin film deposition techniques, plasma-enhanced chemical vapor deposition, PECVD, stands out as a method that effectively utilizes plasma to catalyze chemical reactions, thus enabling the process to occur at significantly lower temperatures compared to traditional chemical vapor deposition, CVD, methods. This reduced process temperature is a key feature of PECVD as it allows for the preservation of thermally sensitive components, making it widely popular in industries such as semiconductor manufacturing. The process begins with the introduction of specific gases or a mixture of gases into a specialized reaction chamber. The selection of these gases is governed by the desired material for deposition onto the substrate. For example, silicon deposition typically involves the use of silane, while methane is used for carbon deposition, and a variety of metal organic compounds are used for metal deposition. Following the gas introduction, radiofrequency, RF, energy is applied. This energy ionizes the gas, leading to the formation of a plasma state. The plasma state is characterized by a mix of charged particles, including electrons, ions, and neutral species. It's noteworthy that these high-energy electrons are instrumental in breaking down the gas molecules into reactive species, an essential part of the PECVD process. The newly created reactive species, which consist of radicals and ions, then proceed to interact with the substrate's surface. The radicals, being highly reactive with a long lifetime and high density, and the ions, capable of breaking down weakly bonded reactive species, lead to the deposition of a thin film on the substrate surface. Unwanted byproducts from these reactions, generally in a gaseous state, are conveniently removed by a vacuum pump. PECVD boasts several advantages. For instance, it exhibits a high deposition rate even at lower temperatures. To illustrate, where thermal silicon nitride, CVD requires temperatures in the range of 800 to 900 degrees Celsius, PECVD can achieve SiN deposition at approximately 350 degrees Celsius. Moreover, PECVD exhibits a unique characteristic when depositing multi-component films. The reaction rates of each component particle tend to be similar, resulting in a relatively consistent reactivity across the different material components. This results in films with good mechanical strength and moisture-blocking properties. Nevertheless, PECVD is not without its drawbacks. The reduced process temperature can hinder the removal of byproducts. The ion bombardment inherent in the process could potentially cause damage. The use of reactive species can lead to homogeneous reactions. Finally, the step coverage can be poor, displaying a PVD-like process, although this can vary depending on the material. High-Density Plasma Chemical Vapor Deposition, HDP-CVD, is a specialized variant of Plasma-Enhanced Chemical Vapor Deposition, PECVD, that employs a high-density plasma source to enhance thin film properties compared to traditional PECVD. One key difference between PECVD and HDP-CVD is the type of plasma source used. PECVD typically uses a capacitively coupled plasma, CCP, source, while HDP-CVD utilizes an inductively coupled plasma, ICP, source. The ICP source allows for higher plasma density, hence the term high-density plasma. This high-density plasma process begins with the introduction of precursor gases into a deposition chamber. The nature of these precursor gases is dictated by the type of film desired. Upon entry, these gases are ionized via a high-frequency RF power source to generate a plasma that's enriched with ions, electrons, and neutral species that will react with a substrate's surface. The application of a high-frequency RF power source promotes the ionization of gases, producing a higher count of reactive species and thus driving an increased deposition rate. This culminates in a high-quality film that offers better step coverage, a feature that's crucial in the semiconductor industry where the conformal coverage of complex 3D structures is paramount. Simultaneously, HDP-CVD deploys a low-frequency RF power source to instigate a biasing effect. This process controls the energy of the ions bombarding the substrate and facilitates the sputtering or etching function. Increasing the bias power enhances the etching effect, allowing for simultaneous deposition and etching. This capability, also known as sputter etching or resputtering, optimizes the step coverage, particularly in high aspect ratio structures, and thus improves the quality of the film formed. HDP-CVD offers a notable level of versatility, enabling the deposition of a wide range of materials, including silicon dioxide, SiO2, silicon nitride, Si3 and 4, and an array of low-K dielectrics. These materials are pivotal in the manufacturing of contemporary semiconductor devices. However, HDP-CVD is not without limitations. The high RF power can induce excessive substrate heating, potentially damaging sensitive components or structures. Moreover, the resputtering process might introduce unwanted impurities into the film. For these reasons, the balance between deposition and etching is of paramount importance, requiring careful control of process parameters in HDP-CVD to ensure high-quality films. In conclusion, HDP-CVD is a critical deposition technology that offers superior step coverage and high-quality thin films. Its role is integral in advanced semiconductor processes and other areas that require thin film deposition. Ongoing research and development in HDP-CVD continue to broaden its capabilities and expand its range of applications. In-situ Dry Cleaning, ISD, is a method that is fundamentally transforming the process of substrate cleaning in semiconductor manufacturing, especially in single wafer tools. This method employs a remote plasma system, eliminating the need for opening the chamber during the cleaning process. It provides a significant advantage in terms of maintaining the integrity of the environment inside the chamber and reducing potential contamination risks. One of the primary methods of ISD is the direct plasma cleaning (DPC) approach, which utilizes a capacitively coupled plasma (CCP) system. Despite its practicality, DPC has some drawbacks. It entails the flow of clean gas into the chamber to generate radicals, leading to simultaneous cleaning. This concurrent process often results in reduced cleaning efficiency and can potentially damage parts due to the high energy of the generated plasma. To counter these issues, the Remote Plasma System (RPS) approach has been introduced, which combines CCP and inductively coupled plasma (ICP) techniques. In the RPS method, plasma is first created in the RPS. Then, radicals from nitrogen trifluoride (NF3) are generated and flowed into the chamber for cleaning. This method allows the pre-generation of radicals, leading to a higher cleaning efficiency. It results in significant time savings and reduces the risk of parts damage. The use of NF3 in the RPS method plays a critical role as fluorine ions, F, released from NF3 react with silicon, Si, to form volatile silicon tetrafluoride, SiF4. This reaction assists in efficient cleaning, especially for removing silicon-based residues. The usage of NF3 has gained popularity as part of carbon reduction initiatives, replacing carbon tetrafluoride, CF4. An alternative cleaning approach that has lost favor is the use of chlorine trifluoride, ClF3, due to its inherent problems. ClF3-based cleaning is known to cause parts corrosion and has limitations in its application to various processes, leading to its phased-out use. The chamber's structure plays an essential role in the cleaning process. For instance, a rounded waveguide without sharp edges is preferred for preventing the accumulation of residues. Residual gas analysis, RGA, is another technique used in conjunction with ISD to monitor the cleaning process. RGA is used to detect SiF4 signals, which are an indicator of the endpoint detection, EPD, of the cleaning process. Furthermore, ISD also finds applications in four-line cleaning, which involves the cleaning of the exhaust line of the process chamber. However, ISD has limitations and may not effectively remove certain materials. For instance, compounds such as aluminum nitride, ALN, and aluminum oxide, ALO, may prove resistant to the ISD cleaning process.
In the realm of chemical vapor deposition, CVD, the term incubation time acquires a unique importance, marking the initial phase of a relatively slower reaction rate prior to entering the steady-state growth phase. This incubation period is integral to the preparation of the substrate surface for subsequent film deposition, which involves an array of processes, including adsorption of precursor molecules, surface diffusion, and possible initial chemical reactions that alter the surface and create suitable sites for the growth of the film. It's critical to grasp the impact of incubation time as it holds significant sway over the characteristics of the resulting film. It could influence the uniformity of the film, as some areas of the substrate may commence reactions earlier than others. Also, it could determine the film's roughness as the film initiates growth on nucleation sites that are formed during this period. The incubation time's length hinges on multiple factors such as the substrate material and its initial surface condition, the type and concentration of the precursor gases, and the deposition conditions, including temperature and pressure. Typically, practitioners prefer a shorter incubation time to produce a uniform film with a smooth surface. Hence, conditions of the CVD process are typically optimized to curtail the incubation time. Yet, in certain circumstances, a longer incubation time may be beneficial, like when the objective is to form nanostructured films or other special structures with high surface area. Notably, in the area selective CVD or selective epitaxy growth, SiGe, incubation time is absolutely crucial. In these processes, a delay, also known as the incubation time, is often observed in the deposition of thin films. This incubation time, along with nucleus growth, essentially shapes the surface morphology and the electrical behavior of the film. Furthermore, it's instrumental for selective growth. The incubation time can depend on the thin film and substrate combination and the deposition parameters. If the delay has a strong dependency on the thin film and substrate combination, it facilitates selective growth, allowing for growth on some areas of the substrate but not on others. This attribute is harnessed in area-selective CVD and SiGe to achieve highly precise, selective deposition of materials. To conclude, the incubation time significantly shapes the initial growth and structural properties of the film in a CVD process. This effect becomes even more pronounced in techniques like area-selective CVD and SiGe, where the control of the incubation time can be leveraged to achieve selective growth. Hence, understanding and optimizing incubation time is a critical facet of the CVD process, especially when precise, selective deposition is required. Selective epitaxial growth, SiGe, is a crucial technique in modern semiconductor manufacturing, and a prime example of its usage is the formation of source and drain regions using silicon germanium, SiGe, in advanced transistor designs. The process begins with the definition of source and drain regions on a silicon substrate, typically through lithographic patterning followed by etching. Once these regions are defined, they act as the growth windows for the subsequent SiGe process. For the growth of SiGe, a chemical vapor deposition (CVD) process is employed. Gaseous precursors, such as disilane, Si2H6, and germane, GeH4, are introduced into the reaction chamber. At elevated temperatures, these gases decompose and react on the silicon surface to form an epitaxial layer of SiGe. To achieve the selectivity, a technique known as alternating gas supply, AGS, is employed. The unit cycle in AGS consists of a SiGe growth step followed by an exposure step with chlorine gas, Cl2. The chlorine exposure step helps to remove any spurious nuclei or deposits formed on the oxide mask, thereby enhancing the selectivity of the SiGe process. A key challenge in this process is the control of the growth rate and germanium concentration in the SiGe layer. The introduction of chlorine during the exposure step can decrease the growth rate, while the preferential desorption of germanium chlorides during this step can lead to an increase in germanium concentration. Interestingly, the flow rates and exposure durations of chlorine do not significantly affect the germanium concentration in the SiGe layer. This offers a level of control over the SiGe process, allowing for tuning of the electrical properties of the source and drain regions. This innovative use of SiGe in forming SiGe source and drain regions can enhance device performance. The varying germanium concentration allows for bandgap engineering, enhancing the carrier mobility in the transistor. Thus, the SiGe process is an essential component in the fabrication of high-performance devices like fin-shaped field effect transistors, FinFETs, and gate-all-around field effect transistor, GAA FETs. Selective area chemical vapor deposition, SiCVD, as the name suggests, is a process that allows specific areas on the surface of a semiconductor chip to undergo material deposition. One of the prime applications of SiCVD can be observed in the fabrication process of Applied Materials' Endura Volta CVD cobalt system, which encapsulates copper interconnects with a thin, conformal CVD cobalt layer, enhancing reliability and scalability beyond the 2x nanometer node. Applied Materials technology represents a significant shift in the copper barrier/seed (CUBS) development, introducing the first material alteration in more than 15 years. It facilitates the deposition of liner and selective cap layers that are less than 20 angstrom thick, improving interconnect yield and reliability. This innovation is the industry's exclusive vacuum-based electromigration mitigation solution and the sole CVD cobalt liner product integrated on the same platform with pre-clean, barrier, and copper seed processes. The surge in demand for sophisticated mobile technologies and complex system-on-chip designs has accelerated aggressive pitch scaling, leading to higher circuit density and a need for high-performance interconnects. This trend has introduced new challenges in achieving the necessary coverage, adhesion, and fill for the production of void-free copper interconnects, which are crucial for device operation. The introduction of Volta CVD cobalt system marks the dawn of a new materials era for extending copper interconnect technology. It aids in copper seed layer coverage by enhancing copper wetting, resulting in a thin, continuous, and conformal layer that repairs discontinuities and helps form a robust seed layer, promoting void-free copper gap fill at advanced nodes. As geometries continue to shrink, resistance increases and copper lines become more susceptible to electromigration, EM, failures. A high-quality bond at the interface between the copper and dielectric barrier layer is pivotal to prevent these EM failures. The Volta system, with its best-in-class selective metal capping process, fortifies adhesion at the copper dielectric interface, thereby improving EM performance by an order of magnitude without increasing line resistance or degrading time-dependent dielectric breakdown. In conclusion, the simultaneous use of Volta CVD cobalt as both liner and selective metal cap enables complete encapsulation of copper lines, ensuring the most robust interconnect reliability for the 2x nanometer node and beyond.
Single wafer CVD tools represent a prominent and versatile subset of the equipment used in chemical vapor deposition (CVD) processes. Designed for efficiency and precision, these tools typically consist of a single chamber attached to a cluster tool, accommodating one wafer at a time. This design facilitates the use of various types of CVD processes, such as thermal CVD, plasma-enhanced CVD, PECVD, and High-Density Plasma CVD, HDP, enabling a broad spectrum of material deposition capabilities. Critical to the operation of single-wafer CVD tools are the precursor materials used for deposition. These can range from inorganic precursors and reactant gases to metal-organic precursors, depending on the desired deposition material. The proper handling and delivery of these precursors is facilitated by a vaporizer for metal-organic precursors, gas cylinders, and a carrier gas system. Precursor flow is carefully controlled using mass flow controllers, MFCs, all integrated within a comprehensive integrated gas system, IGS. The precisely controlled precursor gases are then introduced into the chamber through an injector or a showerhead, where they encounter the substrate held by the chuck or susceptor. Depending on the specific CVD process being used, a plasma may be generated using a capacitively coupled plasma, CCP, for PECVD or an inductively coupled plasma, ICP, for HDP. The gas pressure within the chamber is accurately controlled via an automated pressure control, APC, system, using a pressure gauge and a butterfly or pendulum valve to maintain the optimal process conditions. The exhaust gases, varying potential process contaminants, are then evacuated via a dry pump and routed through a scrubber prior to venting, ensuring a clean and controlled process environment. However, a noteworthy challenge is the possible formation of powder in the foreline, which can impair the pumping efficiency. This impairment necessitates frequent preventive maintenance, PM, reducing the tool's operational time and thereby affecting the overall productivity. Lastly, regular maintenance and cleaning are vital to keep the single-wafer CVD tool operating optimally. This often involves periodic wet cleaning, as well as in-situ dry cleaning, to remove any residual deposition from the chamber and other process components. By understanding these aspects of single-wafer CVD tools, one can appreciate their critical role in achieving high-quality, repeatable deposition processes in the semiconductor manufacturing industry. Chemical vapor deposition (CVD) techniques are vital in numerous thin film applications. Semi-batch CVD is a unique approach that effectively combines the merits of both batch and continuous flow methodologies. As opposed to continuous flow systems, which constantly input and exhaust gases, or batch systems, which introduce all reactants at once and let the process complete, semi-batch CVD involves regular refreshment or replacement of the gas phase reactants, substrate, or both. One of the types of semi-batch CVD is a multi-stage type, which is a single-chamber system but designed with multiple showerheads and chucks, allowing for the simultaneous processing of 2 to 4 wafers. This setup offers mid-throughput capability, with each stage optimized for a specific part of the deposition process. This controlled, stage-specific deposition affords a higher degree of control over the final film properties and increases the efficiency of the system. The spatial or merry-go-round, MGR, type is another semi-batch CVD variant designed for high throughput. Here, the substrate is continually rotated through different zones under a stationary gas cloud, each zone catering to a different part of the deposition process. This type allows for rapid, high-throughput deposition at a larger scale. In semi-batch CVD systems, byproducts and unreacted gases can be continuously or periodically purged from the chamber, while fresh reactants are introduced. This management of gas concentrations reduces precursor waste, leading to better control over the film's characteristics such as thickness, uniformity, and composition. Also, it ensures that byproducts don't interfere with the ongoing reaction or deposit onto the substrate, maintaining the quality of the film. While semi-batch CVD does involve complexities in managing the precise timing and rate of gas additions and removals, it offers the potential for enhanced control over film deposition, uniformity, and efficient material usage. The nuances and advantages of semi-batch CVD processes are crucial for optimizing various thin film deposition applications. Chemical vapor deposition, CVD, is a versatile technique for the production of high-quality thin films and coatings. Among the different types of CVD, batch CVD has long been an established process, especially for large-scale industrial production of thin films. Batch CVD is typically performed in a furnace-like setup, often referred to as a hot wall or quartz dome reactor. This reactor is equipped with heating elements, such as lamps or resistance heaters, that provide the necessary thermal energy for the reactions to occur. The reactor may also have additional components such as gas injectors for the delivery of the precursor gases and an exhaust system for the removal of byproducts and unreacted gases. The substrate on which the deposition occurs, often a silicon wafer, is placed on a heat-resistant boat, typically made of silicon carbide or quartz, for the duration of the deposition process. One of the variants of batch CVD is low-pressure CVD, LPCVD, which operates at reduced pressure conditions. LPCVD allows for better control over the deposition process, improved film uniformity, and it can enhance the quality of the deposited film. However, batch CVD is not without its limitations. There can be significant in-wafer uniformity issues due to gas flow dynamics and differences in exposure of different parts of the wafer to the reactant gases. The problem can be mitigated somewhat by operating in a surface reaction limited regime, where the rate of deposition is controlled by the rate of the surface reactions rather than the delivery of reactant gases. Furthermore, the issue of unwanted deposition on the backside of the wafers remains a significant challenge, potentially affecting the electrical properties and performance of the devices. Finally, wafer-to-wafer uniformity can also pose a challenge, as variations in conditions across the reactor can lead to variations in film thickness and properties from one wafer to another. Despite these challenges, batch CVD, particularly LPCVD, has served as a workhorse in the semiconductor industry for many years. However, with the advancement in CVD technologies and the push for better control over film properties and uniformity, batch CVD has been experiencing a fade-out trend, being replaced by other variants like single-wafer CVD and semi-batch CVD that offer more advantages. For a more detailed comparison between single and batch processes, be sure to check out my video episode titled Fab Part 3, Single versus Batch Process Equipment. Your engagement in this enlightening exploration of CVD basics, a cornerstone of semiconductor technology, is deeply appreciated. As fellow learners, we find your curiosity and commitment highly inspiring. If you found value in this content, please do hit the like button, subscribe to our channel, and activate notifications to ensure you don't miss out on our latest offerings. In our forthcoming episode, we'll be unraveling the core concepts of atomic layer deposition, ALD, examining its process specifics, precursor roles, and equipment, and investigating its merits and drawbacks in the context of semiconductor production's efficiency and quality. Your continued support and enthusiasm truly invigorate our efforts. Stay connected with Semi-Slides as we persistently illuminate the fascinating universe of semiconductor technology. See you in our next episode.